Hello dear students, today we'll discuss regarding physiology of resting membrane potential. It's based on the competency PY 1.8. As per the competency, describe and discuss molecular basis of resting membrane potential in excitable tissues. Objectives of today's lecture is understand the concept of resting membrane potential, explain the mechanism of genesis and maintenance of resting membrane potential, that is, in short, it is RMP, and give the normal values of RMP of different excitable tissues and equilibrium. Basically, as we have learned in the initial lectures of general physiology, human body is made up of almost about 100 trillion cells. Each and every organ is nothing but a bunch of cells. So grossly we divide cells into two categories: non-excitable cell and excitable cell. Excitable cell means those who are having electrical potentials at the cell membrane, and they are capable of generating an action potential and they're electrically active. So these are called as excitable cell. And other cells which are not generating any action potential, or there is no potential at the cell membrane, they are called as non-excitable cells. Now if you can see in this diagram, if you just put up electrode on the surface of any of the cell and insert, you will find that there is a difference in electrical charges inside and outside. So this is called as a membrane potential. So electrical potential difference exists across the membrane of all living cells, with inside being negative in relation to the outside. This potential difference is called membrane potential, and at rest it is called as resting membrane potential. Means in the excitable cell, if you put up any electrode, you will find there is potential difference. So at the resting condition, it is called as a resting membrane potential. And when you are giving any electrical stimulation, polarity will change. Inside will become positive as compared to outside. It is called as action potential. So these are the basic things. So at the rest, when no stimulus is given, whatever potential is recorded at any excitable cell, it is called as a resting membrane potential. Now this potential is different in different cells of the body based on the contents of ICF and ECF in that region. For example, in case of the neurons, it is minus 70 millivolts. In skeletal muscle, it is again minus 90 millivolt. In cardiac muscle, it is minus 90 millivolt. Likewise, there are differences based on the ICF of the cell and the ECF in the surrounding region. Now, what are the basis of generation of resting membrane potential? So we'll learn first, try to understand first the physics behind this. There are four reasons are there. First reason is permeability of the cell membrane, which is selective. Selective means it is allowing some ions to pass easily and not allowing others to easily. So first reason is permeability. Second is Gibbs-Dunance equilibrium. We'll try to understand what is this. These two scientists have explained the phenomena. Nernst equation. And fourth is Goldman-Hodgkin equation. So based on this four, we'll try to understand what is the basis of resting membrane potential in any living cell. So we'll learn the physics phenomena behind this. As I mentioned, permeability. The cell membrane is selectively permeable to ions and other solute particles. Some ions are highly permeable, some are less permeable, and others are impermeable. Okay. So due to this, there is electrical differences generated across cell membrane. So that is the first reason. Then the permeability mainly depends on obviously molecular weight and radius of ions in the hydrated form. So the ions like sodium, potassium, chloride, HCO3 ions are commonly present in the ICF and ECF. Out of this, the permeability of potassium is almost 500 to 1000 times greater than that of sodium. The membrane is practically impermeable to intracellular proteins. which are dominant in a cell. Basically, the cells form of proteins, and some are on the membrane and some are inside, and especially the intracellular proteins, membrane is impermeable, and they are having electrical charges also. So due to this, again, an electrical imbalance is generated. So that is the first reason for potential difference across cell membrane, that is permeability of different ions and substances which are present across the cell membrane. Some are in the ICF, some are in the ECF. Now, what is meant by this Gibbs-Dunant equilibrium? Let's understand a basic physics principle now. When two solutions containing ions are separated by a semi-permeable membrane, at equilibrium, each solution will be electrically neutral. The total quantity of cations will be equal to total quantity of anions. Also, the product of diffusible ions on one side of membrane will be equal to product of diffusible ions on other side of membrane. This is called as Gibbs-Dunant membrane equilibrium. Let's understand this. So these solutions are the solution A and solution B. We are keeping in container and separating it by a semi-permeable membrane. So even if the quantities vary, cations, ions, but what will happen? After some time, there will be electrical balance across cell membrane because of moments across cell membrane, and both solutions will be electrically neutral. So it is called as electrical force. There will be balance will be there. Whatever charges will be same across this one. But this is okay, a physics based on if you take container, but human body is not a container and not a ideal solution. So there are difference will be there. So now you see, when a non-diffusible ions X, for example, is added on this solution, then as per Gibbs-Dunant equilibrium principle, the distribution of diffusible ions will change to maintain again electroneutrality on both sides. So this solution was there, sodium and potassium, sodium and chloride. There we have added an X solution. So now what will happen? See, because of addition of this, electrical difference will be there now. More negative charges here. So there will be net movement of electrical charges from this direction. So it is called as electrical force or electrical gradient created because of this. Now because of this, what will happen now? The chemical concentration will change. So this will create movement in opposite direction. Sodium is more here, less on this side. So it will try to move from area of higher concentration to lower concentration. So this is called as the chemical gradient or chemical force. So net movement will change now. And due to this movement now, after some potential difference, net movement will be stopped when it becomes equal. Okay. So presence of non-diffusible ions on one side of membrane affects distribution of other ions to which membrane is permeable. This results in asymmetrical distribution of ions across cell membrane. This is called as Dunant's effect. In accordance to Gibbs-Dunant equilibrium, asymmetrical distribution of diffusible ions occurs across cell membrane with more cations present inside. Therefore, potassium will try to diffuse into ECF from in ICF, which is opposite to electrical gradient created by presence of non-diffusible ions. Then at equilibrium, what will happen now? Movement will stop based on when both forces opposite each other. So finally equilibrium is reached between concentration gradient and electrical gradient, resulting in diffusion potential across cell membrane, where net movement will stop. So the potential at which net movement stops is called as a equilibrium potential. Now it is different for different ions. It will be different for potassium, different for chloride, different for sodium. So this is for the single ions. So Nernst equation basically explains equilibrium potential for different ions. So it is based on this formula. So details of this formula is given in the next, that is R stand for watt, T, R stand for natural gas constant, absolute temperature, Faraday's constant, valency of ions in its natural logarithm, concentration I means concentration of ions in ICF, concentration O means concentration of ions in the ECF. So for particular ion there will be Nernst equation. But again, human body is a mixed one. You are not a single ion, you have got a bunch of ions. So as you can see the different there are almost this much ions are there, and you can see the here I mentioned they have given in spinal motor neuron. You can see sodium, potassium, these are concentrations. Now when a membrane is permeable to several different ions, diffusion potential that develops depends on three factors. We don't have only single sodium or potassium. We have got sodium, potassium, chloride, calcium. So many are there. So the potential need not find for single. It will be total. In total, what is equilibrium potential? So it depends on polarity of electrical charges of each ions, permeability of the membrane, and concentration of respective ions. Now, based on this, we can find membrane potential across cell membrane at rest for any cell based on concentration of sodium, potassium, chloride across cell membrane. So this is the formula to find membrane potential for any particular cell. So Gibbs, the Goldman's equation or Goldman-Hodgkin equation tells us resting membrane potential for particular cell. Nernst equation tells us equilibrium potential for particular ions. Dunant's effect is explaining it, movement of ions across cell membrane, and permeability will tell us which are permeable, and based on that what are the changes are happening. So V is the membrane potential, R gas constant, absolute temperature, Faraday's number. So like this we can calculate resting membrane potential of a particular cell based on the contents of ICF and ECF. We can calculate the potential by the Goldman equation, and based on this we will see there are different neurons are having a different, skeletal muscle is having a different, and cardiac muscle is having a difference. Now to summarize, we have learned today what is meant by resting membrane potential. So it is membrane potential across cell membrane at the rest without any stimulation. We have explained the mechanism of genesis. 4 reasons are there. One is a selective permeability of the cell membrane. Second is a Gibbs-Dunant's equilibrium. Third is Nernst potential, and ultimately by combination of all ions which are present across cell membrane, by Goldman equation we can find the resting membrane potential. Maintenance of RMP I have not explained, that is the work for you, will be discussed during your class, how the membrane potential is maintained. Normal values have given for 3 tissues, there are so many are there. So in this topic today we have tried to explain resting membrane potential. So here we are finishing membrane potential. Thank you. We'll have a discussion during our lecture now.